Today's Algebra 2 lesson is finding the probability of disjoint events and overlapping events. It's lesson 10.4. Let's talk through a warm-up just to get us familiar with some of the terms you've learned before. Got two situations that are both actually true stories. The first one's about a bus accident. True story. It's probably at least 10 years ago. One of our school buses actually got into an accident driving students to school. Luckily, no one was hurt, just a little bit of damage to the school bus and the car that turned right into it. So you can see here the bus was turning, the school bus was turning, and the car hit the school bus right in the center there. So if we think about it, when the police officer arrived on scene, when they were writing up their accident report, where did they state that the accident occurred? Did it occur on Hill Avenue, or did it occur on the highway? Well, most of us looking at this would acknowledge that, yeah, it occurred at the intersection. You can't just say that it occurred on one of those streets. It occurred on a section of pavement that is actually part of both at the same time. And that indeed mathematically is what an intersection is. If you're looking at the intersection of two events, you're looking at what is common to both. So this section of pavement, it's part of Hill Avenue and it's also part of the highway at the same time. If we were to, let's say, pave Hill Avenue, and then a month later decide we needed to pave the highway, we really wouldn't have to pave this intersection part because it was already paved. We wouldn't want to pave it twice. That would be a bit of a waste of materials there. But an intersection is the section that's part of both. The other scenario I want you to think about former President George W. Bush. Now, he was governor of Texas before he was elected president. And as he was developing some of his campaign slogans, he looked back at what, a lot of people said, and I'm not trying to pose any political beliefs on you, but a lot of people said that he was very successful in Texas when he was the governor, uniting everyone to work for the betterment of Texas. He would say, I don't care if you're a Republican, a Democrat, or an independent, we're all going to work together for what's best for the state of Texas. And he made that one of his many campaign slogans as he was running for president, saying, I'm a uniter, not a divider. So when we think of George Bush, we kind of think about what a union is. It's bringing everything together all in one big group. We're uniting the Republicans, the Democrats, the independents, everybody all together. And the hope was that everyone would work for the betterment of the country. So you've seen two examples of union and intersection in real life scenarios, but those are actually words we use mathematically. We're going today to be looking at the union of, in essence, two probabilities, the two different events going on. And we're going to have to think back to this term of what a union and what an intersection is as we work through that. Now our notation here, this big P, is always going to stand for probability. This is going to be asking you to calculate the probability of event A or event B occurring. But just as with the bus accident, you have to be careful not to count what is in the intersection twice. So I'm going to take you back to some, slightly more elementary examples of uniting sets together using a Venn diagram. So I have two sets for us to look at. Set A is in red, set B is in blue, and if I set it up as a Venn diagram, I could set the red set 1, 2, 3, 4 into its own circle, but then when I unite it with set B, we see that 3 and 4 actually is in the overlap. It's in that intersection, if you will. Now I could look at my two separately and say, set A has 4 elements, set B has 4 elements, so the union of A and B would have 8? No, that's not right. As we look at the Venn diagram, we wouldn't count 3 and 4 twice because they're in both sets. They're in the intersection. So as we even look at our probabilities, we're going to have to know what is part of the event A, what is a part of event B, making sure that if there's any overlap or if there's something, in other words, in the intersection, that we don't count it twice. So what this first example shows you an overlapping event. 3 and 4 are in both sets. Put those in purple because when you mix red and blue, you get purple. The union, however, of the two sets, would only have 6 members in it. You'd take the 4 members in set A, the 4 members in set B, and you'd have to subtract out that there are 2 members that are in both sets. Now let's take a look at another example. Now, this example is going to show us that if there's nothing in that intersection, you have what we call disjoint or mutually exclusive sets. So set A is in red, B is in blue again. And I notice when we map both of them in our Venn diagrams, the union actually does have 6 members in it, taking the 3 members in A, adding into it the 3 members in B. We have a total of 6 members in the union. There was nothing in the intersection. These two sets are disjoint. In essence, they have nothing in common. They are mutually exclusive. As we look at our probability notation, we do need to, when we're calculating the probability of compound events, that means 2 things occurring together, there's 2 separate calculations, just as we saw our calculations with our Venn diagrams and the number of elements. So if we have an overlapping situation, now please note, the problem's not going to say this is an overlapping situation. You have to be able to recognize if you have any members that are in that intersection, So we're looking at what's the probability of event A or event B occurring? Well, you'll add A's probability to event B's probability, but you'll subtract out what was common to both. Now, for a disjoint event, you simply have to add the 2 individual probabilities together. And let's take a look at an example of each of those. What's the probability of drawing either a king or a 3? If someone were to fan the whole standard 52 deck out in front of you and say, pick a card, any card, what would be the probability of drawing a king or a 3? Well, you might want to just make a list of all of the elements in each probability section of each event. Event A is that you want to draw a king. How many kings are there in the whole deck? Well, there's 4. King of hearts, king of diamonds, king of clubs, king of spades. Event B is drawing a 3. How many 3s? Well, there's 3 of hearts, 3 of diamonds, 3 of clubs, 3 of spades. What we clearly see is that there are not any members of set A that are also in set B. So our probability is calculating the probability of a disjoint event, A or B. What is the probability of drawing a king? Well, how many kings in the deck? There's 4 out of the 52 possible cards in the deck. How many 3s in the deck? Well, there's 4 out of the 52 possible. We're just going to add the 2 together. And because I already have a common denominator, I'm just going to add them together, but then I should always reduce my fraction to 2 out of 13. So this is an example of theoretical probability. So we could even look at our final fraction saying, theoretically, if I were to draw 13 cards, only 2 of those cards would either be a king or a 3, theoretically. Let's look at another example. Now let's calculate the probability when we're rolling a standard 6-sided die. I'm curious, what's the probability of either rolling a number greater than 4 or an even number? I'm going to make a list of what those options are. To roll a number bigger than 4 on a 6-sided die, a 5 or a 6 are my possibilities. Not 4, because I'm supposed to be rolling a number bigger than 4. So 5 and 6 would be the 2 numbers on that die that would be bigger than 4. Event B would be rolling an even number, 2, 4, or 6. You don't have to draw the Venn diagram, but just for a visual, I'm going to let you take a look. If I graphed event A and event B, 6 is in both sets, if you will. 6 is in the intersection. It's what's common to both. So this is an overlapping event. So now I know which of the 2 formulas to use as I calculate the probability. I'm going to use the overlapping scenario, and I'll take the probability of event A. There are 2 numbers on a 6-sided die out of the 6 possible that are bigger than 4. Event B, there are 3 numbers on the 6-sided die that are even. Then I have to subtract out that there was 1 number, that number happened to be the number 6, 1 out of all the 6 possibilities that's in both sets. I'm simply going to add my numerators, 2 plus 3, and subtract 1. I get 4, 6, but again, always reduce your fractions. Let's look at one last example. and one last concept to go with it. We're going to look at the probability of the complement of an event. So think about if when you're watching the weather forecast and the weatherman says that there's an 80% chance that it won't rain. 80% chance that it won't rain tomorrow. Which means what is the chance that it will rain tomorrow? Well, a lot of you are probably already thinking in your head, well, it's going to be 20% chance that it will rain. What you actually were doing, without maybe knowing it, you took 100 minus that 80% that you were told about. And that's how you calculate the probability of the complement of event. This notation is the probability of A bar, meaning that's telling me to calculate, in essence, the opposite. So the complement of an event really is the opposite of it. So when I said there was an 80% chance that it wouldn't rain, its complement is the opposite of that it will rain. So I would actually be taking 1 minus that 0.8. Let's look at a math example. What's the probability of drawing a card out of a standard 52 card deck that is not a 7? Well, when they're asking you to find the probability of something not happening, they're actually asking for the complement of the event. So I'm going to take 1 minus the probability of actually drawing a 7. How many 7s are in the deck? There's 4 7s in the deck out of the possible 52 cards. So the complement here, in other words, the opposite, or as it's asking, the probability of not drawing a 7 is 1 minus 4 over 52. I found a common denominator. I rewrote 1 as 52 over 52. Subtract from it 4 over 52. That gives me 48 over 52. And then, of course, I reduce my fraction. And that's the probability, the theoretical probability of drawing a card that is not a 7.